Thank you, Frederic. So yeah, I will basically speak about all those software or libraries. Just as Frederic, it's almost a copy-paste from last year's presentation because there are not much new stuff, but hopefully this is new for some of you. So I will start by giving a quick introduction to how we do parallel computing in FreeFEM, what is PETSc and how to use it, and then I will focus a little bit on more advanced functionalities, and I will wrap things up maybe with some details about domain decomposition methods. Okay, so I think when Frederic asked if anyone was not aware of what FreeFEM was, nobody replied. So I guess you all know that FreeFEM is a domain-specific language for finite elements. And so whenever you need to deal with finite elements, I think you are also aware that we basically need to be able to deal with meshes. We have to define associated finite element spaces, and on those finite element spaces, we can do vector and matrix assemblies, so linear or bilinear form assemblies. And in the end, we need to do algebraic operations. So in FreeFEM, with the standard FreeFEM++ binary, we can perform all this efficiently in sequential. So if you want, one way to do it in parallel is to use PETSc. And so if you don't already have PETSc installed on your machine, we can install it. We install it for you with FreeFEM with the command make PETSc SLEPc. So it's not extremely robust, but it's one way to have it installed, hopefully on most machines. And so it comes with a lot of additional internal packages. So for example, if you use a machine with no MPI implementation, we will automatically install one for you. It's MPI-CH. If you have a brand new machine with no CMake, we will also PETSc will also install it for you, and then FreeFEM will be able to use it. Again, if your machine is from scratch and you don't have Bison, we will install it for you. If there is no BLAS on your machine, we will install automatically OpenBLAS. If you have a machine with Fortran available, we install MUMPS, which is a direct solver. Yeah. Share the screen on Zoom, yes, of course. Thank you. Okay, so if you don't have Fortran available, we install another direct solver, which is SuperLU, which is in plain C, so no issues. There is also a sequential version of SuperLU distributed, which is called just SuperLU, that we also install. SugeSparse is the default Sparse solver in FreeFEM for, I think, about 20 years. So we also install it for you if it's not available on your machine. And then we have slightly more advanced packages. So Hyper is an algebraic multigrid solver. Metis and Parmetis are graph partitioner from the US. Scotch is a graph partitioner from France. TEDGen is a mesh generator. Then we have SLEPc for eigenvalue problem. In SLEPc, we also install RPAC for you if you have a Fortran compiler. We also install HPDDM if you have shared libraries on your machine. And we have also MMG and ParaMMG for mesh adaptation and HTool for hierarchical matrices. So all this is automatically installed for you by PETSc, but it is then installed, it is then used by students. So of course, if you already have your PETSc installation, you can use it, and then FreeFEM will use it. But of course, if you don't, we do it for you. So this is working on Windows, Linux, Intel, macOS, either Intel or ARM, Fujitsu CPUs, and so on and so forth. And so it works both with sequential, so with one MPI process, but also in parallel with multiple processes. So what's important to keep in mind is that you always need to use FreeFEM++ MPI, even if you are running in sequential with a single process, which is slightly technical, and I won't bother with this. So what is PETSc? Maybe you are less familiar with this library. So PETSc stands for the Portable Extensible Toolkit for Scientific Computing. And so it comes with a bunch of additional classes. And most of these classes are actually exposed to FreeFEM users. So if you are a FreeFEM user and you do load PETSc, then you can use almost all of the PETSc library. So for example, you can use the time steppers, you can do a higher order Runge-Kutta, implicit method, implicit explicit method, adaptive time stepping, and so on. You have access also to the nonlinear solver, so Newton with trust region, Newton with line search, variational inequalities, and so on. You have also access to the linear solver, which in PETSc called KSP, so it's and below the KSP, you have the preconditioner, so Schwarzschild, domain decomposition method, incomplete factorization, multigrid, algebraic multigrid, and so on. We also have an interface to the Tao solver, so toolkits for advanced optimization framework. So you can do PD constraint optimization, adjoint-based optimization, interior point method, so on and so forth. So all this is nicely interfaced, and then comes the domain management. So in PETSc, there are many types of domains. You can have Cartesian grid, DMDA. You can have unstructured meshes, DMPlex. You can have forest of trees, DM forest. You can have particles, DM swarm, and so on and so forth. So in FreeFEM, you must be aware that we have only interface with DMPlex, so unstructured mesh. And so this can be used, for example, to use GMSH4 meshes in binary formats. So the GMSH plugin inside FreeFEM is a little bit outdated. We only support version 2 of the meshes. But if you use DMPlex, you can load those kind of meshes, no problem. Okay. So how to use PETSc? The most important point to keep in mind is that the type of a matrix is not matrix, as in the standard FreeFEM script, but math. Okay? And so we provide an easy tool to convert a sequential FreeFEM matrix to a PETSc math. Okay, so I will try this. I will try to show you just on a really simple example. So this is not my laptop, so I hope I will not do too much mistakes. Plus en QWERTY en AZERTY. Okay. Math.edp. So again, you need to load the PETSc plugin. Recently, Frédéric added the interface to define an identity matrix à la MATLAB with the I function. So I will just define a stupid identity matrix. And then you can just do math d. And for example, you can view the matrix using object view. Okay. And so now you can do FreeFEM plus MPI. Math.edp. Okay. And we have a matrix stored in PETSc format. Okay. What's important to keep in mind is that with those maths, you can basically do the same operation as with the matrix. So you can multiply a math with a vector. You can compute the solution of a linear system using the at-1 operator. And you can fine-tune the solver using a string of parameters, for example, S parameters. So in the maths, as they are used to both compute matrix vector or to solve linear system, we also attach a KSP, so a Kryler solver. And so again, you can fine-tune with the S-params keyword, and within a math, you can either view the math itself or the Kryler solver. Okay, so just to again, a really simple example. If I go back to here, okay. I will do, for example, set B S params equal PC type, something really stupid like Jacobi, or not stupid, but simple, Jacobi. And then instead of viewing the matrix itself, I can view the KSP, for example, using object equal KSP.
Les deux accolades.
Well, yes. Okay, and so now I see all the information with respect to the Krylov solver. So by default, PETSc assume that the problem is non-symmetric. So the GMRes is the default Krylov solver, and you can see that we are solving with the Jacobi preconditioner. So PETSc is not a mammal like Frederick, but it's also lazy, and so in practice it's doing all the evaluation in a lazy way. And so, for example, you can see here that the PETSc has not been set up, so information may be incomplete because we have not asked PETSc to solve any linear system, so it's not doing the preconditioner setup because in the end, if you don't need to solve any linear solve, it should not bother setting up the preconditioner. It can be costly, and so it's just done when needed. So in FreeFEM, there is a single type inside the script, which is the mat. But what you have to understand is that under the hood, we have access to a variety of PETSc implementations. So the default type is the mat AIJ, which is for sparse matrices. Then we have also access to SBAIJ, which is for symmetric matrices. We have access to mat-H2 for hierarchical matrices. We have access to matnet for matrices defined by blocks. Matshell, which are for matrix-free operator, where the user defines its own matrix vector product within the FreeFEM scripts. We have also dense matrices, composite matrices, which are a product or a sum of different matrices which are not evaluated explicitly, but instead evaluated implicitly. Matrices for non-overlapping domain decomposition method, and mat transpose, which is used to represent the transpose of a matrix with not assembling it explicitly. So to go parallel, in FreeFEM, as Frederick mentioned, there is currently no shared memory implementation, so we don't currently support OpenMP inside FreeFEM directly. You are free to use it inside the direct solver, but that's something else. And so in practice, we use NPI, so we use a distributed memory paradigm. And that means that as of today, it's not fully transparent to users. And so we need to use a couple of lightweight macros that are used to do the domain decomposition and the workload distribution. So just an important reminder is that there is a full list of examples using either PETSc, SLEPc, HPDM in the folder example HPDM. And as Frederick mentioned, for the list of new functionalities or bug fix, you can check the changelog.md on the GitHub website. So what's important to mention is that most of the current development are user-driven, so you must ask us what you want. And so in practice, as Frederick mentioned during this morning, we have recently added an interface to MMG2D if you want to try something else than adapt mesh. So this was mostly asked by Paoli. We have also added distributed output on surface mesh. This was done by Pierre. And we have also added a couple of parameters to the MMG2D interface. So this was done by Chris Douglas.
So what do you mean by distributed output?
So this means that in FreeFEM we have an interface to ParaView, which can be used to output solution or meshes. And by default, the interface works on the global mesh. And so Pierre has the possibility of outputting various solutions on different mesh, on different subdomains, and then generate a main file which will automatically load up all the distributed mesh for you in ParaView.
Oh, okay.
Yeah.
But I didn't get when I looked at it. I was not sure.
No, it was I think one of your requests actually. Okay. And so if you don't attend the expert tutorial this afternoon and tomorrow afternoon, you can go on this website. And so it's quite a lengthy tutorial. It's about 200 pages, but it gives you the full picture of how we do parallel computing and how we do it more precisely in FreeFEM. Okay, so some advanced functionalities. So first, I will talk about non-standard eigensolvers. So these have been there for quite some time. but it's always nice to see that we have a quite good interface to SLEPc, which is a package for solving eigenvalue or singular value problem. So in FreeFEM, it's possible, and there are actually some examples to solve nonlinear eigenvalue problem. So currently, the nonlinearities are only in the eigenvalue, so it's still an open problem to define good eigensolver where the nonlinearity is in the eigenvectors. So to solve such an eigenvalue problem, you can define a nonlinear operator T, and then you can use the NEPsolve routine inside your FreeFEM code. There is a special kind of nonlinear problem which are polynomial. In this case, we use PETSc, so polynomial eigenproblem solver. And we can also solve a singular value decomposition problem with the SVD solve routine. And so all these work either in sequential or in parallel. And of course, we can solve standard or generalized linear eigenvalue problem. So there is a recent review paper about the new functionalities of SLEPc. So if you are interested in more details, you can check it out. What's important to keep in mind, again, is that we want you to make as little change as possible when switching from a sequential to a parallel script. And so in plain FreeFEM, when you want to define an array of metrics, you need to use matrix bracket int. And so it's exactly the same in PETSc. If you want to define an array of PETSc math, you just do math bracket int. So the syntax should be familiar to most of you, hopefully. If you know that in FreeFEM, to define an array, we need to use the bracket int bracket syntax. Okay, so now I will focus on some other problems, mostly coming from solving linear systems. So this is, again, this is not quite new, but we've made good progress, and there have been some recent improvement to use those tools more efficiently. And so as a toy problem, I will, for example, assume that we have discretized the Gaussian equation, which then gives a saddle point system, saddle point-like system where we have a block for the velocities and a block for the pressure. And so one of the strengths of FreeFEM syntax is that we can easily define matrices by blocks. Okay, so this is actual running FreeFEM code. And you can see that instead of a matrix, I use a mat, but the same syntax is okay. It can be understood by FreeFEM. Of course, there is a semicolon missing, but that's not the point. So in FreeFEM and then in PETSc, we handle such block systems by using what we call a mat nest. Okay? And so a mat nest is a collection of different blocks of matrices. And so we can see here that we have a matrix defined by a 2x2 structure. And those matrices can be of different type, of different sizes, but they must be defined on the same communicator, the same MPI communicator. So you cannot have one distributed matrix and one sequential matrix. But what's important to see here is that, for example, we use the standard AIJ structure, so sparse matrix for F, B, and C. But for B transpose, we use the type transpose, okay, which does not actually assemble B transpose, but which keep an implicit representation of the operator, such that we don't have to pay the memory price of storing both B and B transpose. We just have a view of B, and then everything is done automatically for you by PETSc under the code. Okay, so one kind of preconditioner for such a problem is what we call the pressure convection diffusion preconditioner, which is based on an approximation of the Schur complement. Okay, so if you don't know anything about linear solver, I'm sorry, but it's not really the point of the lecture. It's just to show you that we can do advanced stuff easy. And so the approximation of the Schur complement is given by this formula, where you have a product of inverses and matrices. Okay. And so in FreeFEM, it's actually quite trivial to define. We just need to define a func, okay, so a standard function, which as an input takes a vector, okay, so an input vector. And then on this vector, we need just to apply this sequence of operator. So we first solve the linear system. So remember that the healthy Krylov solver are called KSP. So when you need to solve a linear solver, you call KSP solve. Recently, we have added the possibility to do the solve in place. So here you can see that we are really using the in vector. So this is the first part. Then we multiply by FP, so mathematical FP, and then we solve the linear system with a math matrix. So these are easy systems to solve. You can use additive sharp multigrades. It's not really technical, but anyway, you get this. And so this defines a function. And so then we say to PETSc, okay, when you want to solve linear systems involving the shear complement, so the block C here, instead of doing whatever you do, you give the hand to FreeFEM, and FreeFEM computes the inverse or apply the preconditioner using a shell. So the shell is just the matrix vector definition. And so here you can see that as a preconditioner, I put the PETSc function, which is the same name. So this works for other types of matrices. So for example, this is if you want to do FEM-BEM coupling. So this is even more technical in the sense that here we have a coupling of finite element matrices and H2 matrices here and there. And so if you look at the MapNest, you get a view like this. So for the FEM block, we assemble an AIJ matrix, just as usual. For this block, we don't assemble it explicitly. We represent it as a composite, so as this operator, in fact, the multiplication of two mats, but not assembled explicitly. The FEM to BEM operator is a standard AIJ matrix, and then for the BEM block, we assemble using a standard matrix H2. Okay. So you can do really, you can play around with different type, different solver, and so it's quite efficient. So about 1 month ago, we added also support for dense blocks inside a matrix. So if you do this in FreeFEM, let's assume that A is a sparse matrix and D is a dense block. So a dense block is a real int. Okay, so you imagine that, for example, you have multiple Lagrange multiplier in an under constraint problem. So when you assemble this, when you write this down in FreeFEM, it can be quite costly because in practice we assemble a sparse matrix explicitly by converting the D blocks as sparse matrices, even if they are dense. Okay? So if you have many columns in D, it can be a little bit costly. If you write this with a math, the D transpose is just again stored with the same representation as D. And so we don't need to convert those operators to sparse matrices. They are kept implicitly in memory, and so it's much more economical. Furthermore, since version 3.20 of PETSc, we can directly feed this operator to a direct solver such as MEMS, so there is really low memory overhead. Okay. And so in practice, it has been used for Stokes problems. I think you will hear more about this this afternoon in Loic's talk. So now I will talk a little bit more about domain decomposition method. And so why do we care about domain decomposition method? If you are interested in solving large problems, you are at the beginning mostly using direct solvers because it's the easiest and most convenient type of solvers. But if you look at their complexity, you see that it's not that good. So in practice here, you can see two problems that have been generated using FreeFEM. One is the system of linear elasticity, and the other is the system of Stokes. Okay, so this is 3D, and this is lowest order finite element. So P1 for elasticity, and P2 for Stokes. So this is done with a sequential solver, but it's MEMS, and so MEMS is kind of the state of the art when it comes to direct solver. So you have access to MEMS inside FreeFEM. And so basically, you can see that as you increase the number of unknowns, so when you refine your mesh, or if you go to higher order finite elements, you will have a blow up in terms of time. And so, for example, if you look at a problem of around 5 million unknowns, it takes more than 1,000 seconds. So it's not really tractable. And so, if you are interested in fine scale problems, it can be quite problematic. So this was done in sequential. So if you use, for example, MEMS sec, you will get exactly this using a standard script from FreeFEM. Of course, you can also use nums in parallel. It's one of its trends. Doing an LU factorization or a Cholesky factorization in a distributed framework is quite technical. Okay, the nums people have been working on this for about as long as FreeFEM, so about 20, 30 years. So it's a really nice piece of software. But still, with direct solver, it's really difficult to make the problem scale. Okay, and so as you increase the number of processes, you will see that the time to solution does not scale ideally. And so in practice, so this is for the largest problem of around 5 million nodes. You see that if you have a machine with more than 64 processes, you are just wasting your time if you try to increase the number of processes. It does not scale that way. So those methods are extremely robust. They can solve almost arbitrary problems, but it's really difficult to make them scale ideally. So they have been trying to put some work into turning this exact factorization into more approximate factorization. So for example, there is a really nice feature in nums which is called block low rank, which turns the exact LU or exact Cholesky factorization into an approximate factorization. But for example, here you can see that first, it does not solve the problem of efficiency. You still don't scale really well when you increase the number of processes. And second, you turn your direct solver, which converges in a single iteration, or with no iteration, just one forward, backward solve. You turn your method into a more approximate solver. And so in practice, for this problem, it's 15 iterations to solve the system. Okay, so at the beginning, you had something which was really robust. You didn't have to worry about anything. We are just doing one forward and one backward. And so now you turn it into something which is more approximate, and so it's more difficult to tune your solver. So then comes domain decomposition. Okay, so this is just a small cartoon. We assume that we are solving for example, Poisson equation on the domain omega. So with FreeFEM, we generate a system X equal B. And the idea of domain decomposition is to decompose this problem, for example, in two subdomains, omega 1 and omega 2. And then we can define sets of operators that are going from the global domain omega to just one subdomain, omega 1 or omega 2. And with the transpose, we can do the other way around. And this can be used to define different kinds of preconditioners. So for example, the additive Schwarz method, which is the default preconditioner in PETSc, in fact, where instead of inverting or computing the LU or Cholesky factorization of the matrix A, we are just computing the LU factors or Cholesky factors of a restricted matrix of much smaller dimension. Okay, so I won't go too much into the detail, but there is a variant of ASM which is called restricted additive Schwarz, which is working slightly better numerically speaking. So the issue is that there is no guaranteed scalability for a large number of subdomains. And so in practice, as I said, the default preconditioner in PETSc is something which resembles the additive Schwarz method. And so if you take your script and go parallel and don't touch anything, at one point your script may be stuck, and it's just because your linear solver is not converging. Okay? So don't forget to always use LU or Cholesky when you start doing some numerical investigation. And so in practice, there are ways to tackle the problem of large number of subdomains, capital N, by introducing a course correction. Okay. So the course correction is basically defined in 3 steps. First, we define local operators on each subdomain. Okay. If you want more detail, we will speak later on about this. But then you can local operator. We can define a global matrix Z, which is the concatenation column-wise of those local operators. And this global matrix Z can then be used to compute a Galerkin product, Z transpose AZ. And so this is something which is not specific to domain decomposition method. You will also have this kind of operator when you do reduced order modeling, when you do multi-scale finite element, when you do multi-grid methods, so on and so forth. So this is a pretty general framework. But in the context of domain decomposition method, once we have assembled this operator AC, we can use it to improve the convergence of the one-level ASM method, for example, using an additive correction. Okay, so the $1,000,000 question is how to choose the number of vectors that we want to have on each subdomain, and how to choose those columns, what to put inside WI. It's still an open question, of course. And in practice, we want to be able to define a preconditioner where the AC operator is the smallest possible. And so to have the smallest AC possible means that we want to have a really aggressive coarsening. And we also want to be able to define a preconditioner which will be able to capture the difficulties of the operator A at a moderate cost if possible. So HPDDM is a library which basically implements all this. It was done during my PhD thesis, in fact. So I think I was not there for the first FreeFEM days, but since 2013, I think I've been there. So almost first, but not quite. And so it was recently interfaced with PETSc. And so what's nice is that, so it works on arbitrary kind of meshes. For example, Q1 here is no problem, or Q2 or whatever. But inside FreeFEM, what's important is that we automatically feed the necessary operators to the preconditioner. So basically, FreeFEM users don't have to worry about all the machinery of the preconditioner. It's automatically done for you under the hood. And so since the integration of the library inside PETSc, we have also been looking at defining algebraic variants of those preconditioners. And the end goal every time is to define adaptive preconditioners. And so what is the definition of, how to explain what is an adaptive preconditioner? We basically want to be able to define a preconditioner which can solve systems. So for example, here I'm using a matrix from the sparse matrix collection. But the idea is that if you use something like additive Schwarz method or restricted additive Schwarz method, those methods will not be very robust. Okay? And so you need to add some course correction or some multi-level scheme. And so how it's done in HPDDM is through solving eigenvalue problems, where we use a threshold criterion tau, which is then used to select how we do the coarsening. And so the more we select, so the higher tau, the faster the convergence. But of course, it's always a matter of trade-off. So the faster you converge, the bigger the coarse operator. Okay, and so this is a common problem when it comes to preconditioner. You have to find the correct balance between convergence speed and setup speed. And so this is, whenever you go parallel, this is something quite common. Okay, and so it's important to keep in mind that when you use PETSc inside FreeFEM, we have also access to multi-grid solvers. So for example, Boomer IMG, which is a solver from Lawrence Livermore National Lab. So you can use it inside FreeFEM through PETSc. And there is also JMG, which is another kind of algebraic multi-grid solver. So these methods work quite well. Okay, so if you are solving stuff like Poisson systems, a system of linear elasticity in FreeFEM, you can use those. They scale extremely well. But there are some other problems, for example, algebraic systems of equation, which are much more difficult to solve. And in practice, it's often the case where domain decomposition method can converge, whereas multi-grid method cannot. Okay, so it also works for nonlinear problem. So this is the Bratoux equation solved in FreeFEM. And so again, we have a nice connection between FreeFEM, PETSc, and HPDDM, such that at each linearization point of the Newton method, we automatically assemble all the tools and all the operators needed by the preconditioner to define a really robust method. So you can see the convergence for each linear system. So we have 4 steps in the Newton method, and every time it's converging quite well. And everything is hidden to the user. The assemblies are done automatically, and you don't have to worry about hooking up FreeFEM with PETSc SNES solver, with PETSc HPDDM linear solvers. So actually, I did not mention in the slide, but I think this is the example /HPDDM/Bratoux 2D Bratoux HPDDM 2D PETSc or 3D PETSc. And so more recently, in fact, a couple of months ago, we also extended the library HPDDM to handle systems of saddle point problem. So the theory is from a paper by Frédéric, Nataf, and Pierre. And so again, all this is quite technical, but what's important to keep in mind is that everything is hidden to the user. And so in practice, I won't go too much into the detail, but the idea is to first define the preconditioner for the A00 block. So this is usually easy because the block is usually symmetric positive definite. So everything that I've presented so far applies to the A00 block. And then we can do a sequence of approximation such that in the end we have a preconditioner for the Schur complement. Okay. I will skip all this, but if you want more details, you can look at the paper. And so in practice, it's quite easy to use. We use the field split infrastructure of PETSc, which will split the matrix into a 2x2 structure. We can define a good preconditioner for the A00 block, and then a good preconditioner for the A11 block. So one thing I did not mention is that PETSc as FreeFEM is implemented in C or C++, and so we use zero-based numbering. And so whenever you see field split 1, it means that you are looking at the bottom right block. So if you want, there is an example for solving Stokes equation, and there is the same for elasticity. Okay. So just to wrap things up, I've tried to present some tools that can be used to define the multi-physics solver if you want, and all this rely on two important points. With FreeFEM, we have a really nice abstraction of the PDEs. We can really define really complex operator, but quite nicely, and with a structure that resembles what we have at the math level. And then we can feed that. We've done the necessary plumbing to feed that to PETSc and to use the versatile tools of PETSc. So the two together can be combined to really composable solvers. Whatever you design in FreeFEM with PETSc can be then transposed to some other code. So for example, during coffee break, I heard about Dolphin, and so Dolphin use PETSc. So if you have some good solver in PETSc, it's usually just a matter of copy-pasting a set of strings and then put it back into Dolphin. I think tomorrow there will be a talk about Rodin. Rodin use MFEM, MFEM use PETSc. So the same machinery, you just copy-paste your string of parameters and then you are good to go. If you want to know more, again, you can look at the tutorial. And again, I will emphasize that if there are things that are breaking or that are working, it's also nice to hear. If you want new features, you can ask us, and so we can be reached either for FreeFEM on the community forum, as Frédéric mentioned. If you have issues or concerns or comments about PETSc or SLEPc, that their respective website as well, and I'll be also happy to answer any issues with respect to HPDDM on GitHub. Thank you.
Question, comment, remark, and also from the web, from Zoom.
I have a question regarding the whole parallel realization. Which stages or how is the parallelization handled at different stages? Because naturally you have the linear solving, which is in parallel, the assembly, which might be not in parallel or not so clear how to parallelize, and then the domain decomposition.
So it all depends. So we have two main stages. The two main approaches. The first approach is you load a centralized mesh. So this is sequential. This is done usually by one process. Then we call some standard graph partitioner like matrices or Scotch, which is in charge of decomposing the domain, the initial domain. And after that, everything is carried out in parallel. So the assembly, the linear solve, the post-processing can be done in parallel with ParaView. You have also tools to go back to the global initial mesh. Okay. Then there is also another approach where you can actually load directly distributed input files so that you don't have to load an initial global mesh. And so everything is done from start to finish in purely parallel manner. we have also tool to centralize or to distribute mesh, to centralize on the sub-communicator of the global communicator. I mean, it's quite involved, and
So
so
it's at the mesh level where the parallelization is, meaning, for example, if I had a centralized mesh,
uh-huh.
and I wanted to do parallel assembly of the centralized mesh, could this also be possible?
So this can be, yes, so this can be done either with this interface or also what Pierre showed this morning. The mesh is kept centralized, and then we do the assembly in parallel, but it's hidden to the user, and we also solve the linear system in parallel, but again it's hidden to the user, and we give back the solution in a centralized fashion.
So, no more question. So thanks again, Pierre.
A question, please. I have tried Maxwell 3D. It's in parallel, I think, example, and
Yes.
it doesn't work. I have tried to make it in a sequential, and it doesn't work also. Is that because parallelism don't work with Windows, or?
Okay, so first, if something doesn't work in sequential, there is really little hope that it will work in parallel. But okay, just small comment. So you mentioned two different things. One thing was with respect to Windows and parallelism in Windows. So I think this part is mostly covered. We have a nice support of parallel computing in Windows. And so the other part was with respect to Maxwell not working in sequential. You'd have to be a little bit more specific because it can be an issue with the solver, it can be an issue with the discretization, it can be an issue with the mesh. So can you expand a little bit on your question? Or?
No, it is an example in a parallelism.
Within the distribution?
Yes, in the distribution, yes. And okay. I have tried to run it in parallelism, but it's not installed in my Windows station. So okay. I've tried to modify the program, the code, into a sequential, but it doesn't work. And is it possible to adapt parallel code into a sequential code?
It should be. In fact, if you run a parallel code with just a single process, it will be a sequential code. But there may be an issue with the installation on Windows. So I've looked at your name, and I will reach out to you in private so that we can see if we can make any.
Yes, thank you.
You're welcome.